All right, this is a continuation of section 5.4 looking at conditional probabilities. So we've got social media is our next question. So adult Americans ages 18 years or older, we're asked whether they use social media, so Facebook, Twitter, and so on, regularly. And we've got this table of information that resulted from that survey. And so notice horizontally, we're looking at uses social media, does not use social media. And then vertically are our age groups. So the total number of people in this study were 530. And we want to know what's the probability the randomly selected adult uses social media given that they are 18 to 34 years old. So when it says given that they're 18 to 34, we now fixate in this column. We know that they are an 18 to 34-year-old. So now, instead of being out of 100 or 530, we're out of 150 total people because we know that they're 18 to 34 years old. And so what's the probability that they use social media? Well, 117 out of the 150 use social media. So this would be 117 out of 150. So this would be the probability of social media given that they are 18 to 34 years old. And sorry, I should squeeze this right here. It's about 0.78 or 78%. Okay, the next one is what's the probability the randomly selected adult is 18 to 34 years old of age given that they use social media. So now it's given that they use social media. So now we know they use social media. So we're now fixated on this row. What's the probability that they use social media? So they're 18 to 34-year-olds. There are 117 of them out of the total 338 that use social media. So this would be 117 out of 338, okay, which is 0.34, whoops, yeah, 346. Okay, and that was the probability that someone is 18 to 34 given that they use social media. So notice that if you switch what's given, the probabilities do not stay the same. So like I can't just switch these two and keep the same probability. Those can definitely change. Okay. So then now we want to know, are 18 to 34-year-olds more likely to use social media than individuals in general? So this question, we just want to look at what's the probability someone uses social media in general. And the social media users, there's 338 out of the 530. So we take 338 out of 530, and that is 0.638. So that is definitely smaller than the 0.78. So we'd say the probability that someone's a social media user, given that they're 18 to 34, that probability is greater than just the general probability that someone is a social media user. And so they are more likely if you're in that age group of 18 to 34. Okay, so now let's suppose that 2 cards are randomly selected from a standard deck of 52 cards. Okay, again, same standard deck, 4 suits, 2, 3, 4, 5, 6, 7, 8, 9, 10, Jack, Queen, King, and Ace. So what's the probability? The first card is a club, and the second card is a club if the sampling is done without replacement, meaning you pick a card and then you keep that card out of the deck. So, what this question is asking, well, what's the probability of getting a club on the first one? Well, let's see. So this is the probability of getting a club and then a club when we don't replace. So this will be the probability that you get a club on the first draw times the probability that you get a club on the second draw, given that you've already selected one club. So hopefully you can see that this is going to be conditional and dependent because once you draw a card and if you don't put it back, it changes our sample space. Okay, so this is going to equal, the probability of a club is 13 out of 52, because there are 13 out of 52 chances. And then we're going to multiply that by, now we know in the first draw we've selected a club, so we're down to 12 clubs because we've taken one of the 13 out. We didn't replace it. There are only 51 cards that are remaining. So this is the given part. Given that we've selected a club already, what's the probability of getting a club? Well, we're down one card in our sample space, and we're down one club, so 12 out of 51. Okay, and if I multiply those together, then I get, it does reduce down to 1/17, which is 0.059. Okay, so that's without replacement. Now, part B wants to know, what is the probability that the first card is a club and the second card is a club if this is done with replacement? So this is the probability of a club and a club, but we replace the club. So we take a card, we look at it, we get a club, we put it back in the deck. So the probability for the first club is still the same, 13 out of 52. However, now we're just putting the club right back in the deck, so we shuffle it up. So that still has the same probability of 13 out of 52 because we haven't changed the sample space. And so this is actually reduces to 1/16, which is 0.0625. So notice how the without replacement changes that probability of getting two clubs. If we keep the card out, it's different than if we look at the card and put it back into the deck. And hopefully that makes sense in your mind, but now we can see the math behind it as well. Okay, so now we're going to be looking at smokers. So according to the National Center for Health Statistics, there is a 20.3% probability that a randomly selected resident of the United States, ages 18 years older, is a smoker. In addition, there is a 44.5% probability that a randomly selected resident 18 years older is female, given that he or she smokes. So what's the probability that a randomly selected resident of the United States ages 18 years of older is female and smokes? So now we're looking for what's the probability that they're female, and I'll just say capital S for smokes. So now, what information do we know here? So the first thing we know is the probability that someone is a smoker is 0.203. So that should be a probability that someone's a smoker. And the probability that someone is a female, given that they smoke, okay, we know that is 0.445. So this is going to be the probability that someone's a smoker times the probability that someone is a female, given that they're a smoker. So this would be 0.203 times 0.445, which is 0.090. Okay. Now the last part of the question is, would it be unusual to randomly select a resident in the United States ages 18 years or older who is female and smokes? Well, 0.090 is greater than our threshold of 0.05. So again, anything less than 5% or 0.05 is considered unusual. But this is greater than, so this would not be unusual. So not unusual here. Again, because we're above that threshold of 0.05 or 5%. Okay. Let's see. So last question here. Just double check my time. I'm doing good. So the following data represents political party by age from a random sample of registered Iowa voters. So our population would be Iowa voters. So we want to first know, are the events Republican and 30 to 44 independent. So we need to just justify the age. So what we're going to do is first let's just figure out what's the probability someone is a Republican, just in general. Okay, so the number of Republicans, there are 2,200 out of the 4,000 individuals surveyed. So we'd say 2,200 out of 4,000. Okay, and that's 0.55. Okay, now to check to see if they're independent, the Republican in age 30 to 34 or 44. Well, let's see if things change when we say what's probably that you're Republican, given that you are in the age range of 30 to 34. So now we're going to fixate. We're going to fixate on this column, 30 to 44. So there are 724 people in this group, and 340 of them are Republicans. So that probability is going to be 340 out of 724, which is equal to 0.47. And so notice that the probability that someone is a Republican is not equal to the probability that they're Republican given that their age is 30 to 44. So when those are not equal, then we would say these are not independent. Or you could say they are dependent. Okay, so that was part A. Part B are the events Democrat and 65 plus independent. Okay, so let's look just, what's the probability that someone is a Democrat? That would be the 1,800 total Democrats out of the 4,000 people. Okay, and that reduces down to 9/20ths or 0.45. So then we want to know what's the probability that someone is a Democrat given now that they are 65 plus. So we are fixating on the 65 plus group. So there are 459 Democrats out of the 1,020 in that 65 plus group. So this would be 459 out of 1,020, which actually is 9/20ths, 0.45. So that tells us that they are independent because those probabilities are the same. And this is based off of the data that we can see here. Okay, answer C. Are the events 17 to 29 and 45 to 64 mutually exclusive? Okay, these certainly are mutually exclusive because you cannot be 17 to 29 and 45 to 64. In more mathematically, you'd say, what's the probability that someone is age 17 to 29 and age 45 to 64? Well, that's definitely going to be 0. You can't have both. You can't be in one age group and another. Okay. Now for part D, we want to know, are the events Republican and 45 to 64 mutually exclusive? So we're going to look at the probability that someone is a Republican and 45 to 64. And if this is equal to 0, then they are mutually exclusive, meaning they can't happen simultaneously. But let's look at, so this would be the probability of a Republican times the probability that someone is 45 to 64, given that they are a Republican. So the probability that someone's a Republican is, again, our 2,200 out of 4,000. That's just from the entire group, probability that you're a Republican, 2,200 out of 4,000, times now the probability that you're 45 to 64, given that you're a Republican. So now, given that I'm a Republican, okay, there are 1,075 in the age group of 45 to 64 out of the 2,200 total Republicans. So when I multiply those together, I get 0.269. And this definitely is not equal to 0. So those two are not